Hi, this is TW Huang. Today, I'm going to talk about recursive task parallelism in Taskflow. This is a very powerful model in Taskflow to help you parallelize recursive algorithms. This is the takeaway for today's presentation. First, we will learn how to program recursive task parallelism in Taskflow and understand the role of cooperative execution in recursive task parallelism. Then, we will showcase two real-world applications of recursive task parallelism. Finally, we will conclude the talk. Recursive task parallelism, or RTP, expresses the parallel pattern where a parent task recursively spawns multiple child tasks and joins their executions. RTP is a very powerful programming model for parallelizing irregular workloads, like algorithms that leverage divide and conquer to solve problems. We recursively partition a problem into smaller blocks of interest. Each partition block then spawns final grand tasks. Finally, we join when interested regions stabilize or reach the base case. Examples of RTP include graph traversals, recursive search, adaptive mesh, matrix multiplication, dynamic programming, and so on and so forth. That is why mainstream parallel programming libraries all support RTP, like Taskflow, OpenSilk, TBB, and OpenMP. RTP in Taskflow is primarily supported by runtime task, which is a task that takes a reference to a TF runtime object created by its running executor. A runtime task allows you to interact with the scheduling runtime, where you can perform asynchronous tasking, cooperative execution, and other things that are only available at runtime. More importantly, all tasks spawned by a runtime task are parented to that runtime task, so you can explicitly join child tasks at any parent or ancestor in the code tree of a runtime task. For example, on the lower left, I have one runtime task that spawns an asynchronous task and joins its execution using code_run. On the right-hand side, I repeat this process recursively and stop at the second level. Runtime task has a very important feature to know, that is, all tasks spawned by a runtime task are implicitly joined at the end of each scope. For example, here I have a runtime task A that spawns 1,000 silent async tasks. When A finishes, these 1,000 silent async tasks are guaranteed to finish because there is an implicit synchronization barrier when the runtime is destroyed. We can also create a dynamic task graph within a runtime task using dependent async tasks. For example, during the execution of the runtime task X, we create a dynamic task graph of 4 tasks, A, B, C, and D, where A runs before B and C, and D runs after B and C. When X finishes, the dynamic task graph created by X is guaranteed to finish because of the implicit synchronization of the runtime task. Another recursive task parallelism supported by Taskflow is task group, which is a more self-managed mechanism than TF runtime to perform RTP. By self-managed, we mean you can explicitly create a TF task group inside a task rather than receiving as an input argument. Similar to TF runtime, you can perform asynchronous tasking and cooperative execution from a task group. More importantly, all tasks spawned from a task group are parented to that task group, so you can explicitly join child tasks at any parent or ancestor in the code tree of a task group. In the example below, I recursively create 2 task groups and explicitly synchronize them using code_run. It's important to understand a few semantic details of a task group so you can avoid misusing them. First, a TF task group can only be created inside a task context. Otherwise, a non-worker thread may mistakenly participate in a work-stealing loop of an executor, which will result in undefined behavior. For example, in the code below, attempting to create a task group outside a task context will throw an exception. While a task group must be created by an executor, the executor does not assume any ownership over the task group. It is therefore your responsibility to ensure that all tasks have finished before leaving the scope of their parent task group. For example, in the code below, forgetting to synchronize the 2 async tasks before destroying the task group can result in undefined behavior. Now, we are going to understand the role of cooperative execution in recursive task parallelism. As you have already seen, runtime task offers a co-run method to perform cooperative execution. Similar to executor's co-run, the calling worker of the runtime will cooperatively execute other available tasks while waiting for all tasks spawned from that runtime to complete. To be more specific, the caller worker cooperatively participates in the execution by helping other workers in the executor to make the overall progress. For example, on the lower left, I create a task flow of 1,000 tasks, where each task submits a new task flow using non-cooperative execution. When you call wait, there is a chance that the operating system will preempt the calling worker until the corresponding task flow finishes. However, if all workers are preempted, no tasks will be able to run, leading to the deadlock. To avoid this problem, we can use co-run from a runtime task, as shown on the lower right, to cooperatively run these 1,000 task flows, allowing workers to continue performing useful work cooperatively through work stealing. With cooperative execution, we can co-run asynchronous tasks from a runtime task, while preserving the caller's execution context and stack state. This is important for us to implement recursive algorithms that need to post-process the results from recursive calls. For example, we can implement Fibonacci algorithm in parallel using runtime tasks. The runtime task spawns two asynchronous tasks to compute 5n-1 and 5n-2, and each of the two asynchronous tasks can also be runtime tasks to recurse to the next Fibonacci level. This diagram shows the execution from the previous slide, running on the Fibonacci number 4. There are a total of 9 asynchronous tasks, one for each node in the call tree. For recursive algorithm like Fibonacci, we can actually reduce the overhead of asynchronous tasking using tail optimization for one recursive call. Instead of spawning a new asynchronous task for 5n-2, we compute it directly in the current runtime task. This reduces the number of created asynchronous tasks, which improves the performance dramatically. At the same time, the left recursive call still runs asynchronously, and we maintain the same parallelism without paying the full cost of 2 new tasks at each level. This is the execution diagram with tail optimization. Only when we move to the left child will we create an asynchronous task. In this example, there will be a total of 5 asynchronous tasks created, which would otherwise be 9 without tail optimization. To understand how good the tail optimization is, we measure the performance of finding different Fibonacci numbers up to 40 on the 16 threads. And we observe up to 2x runtime improvement over the implementation without tail optimization. This large performance improvement is due to the largely reduced number of asynchronous tasks by tail optimization. For example, at the 40th Fibonacci number, tail optimization allows us to reduce the number of tasks by 2x. This slide shows the implementation using task group, which is basically similar to the one implemented using runtime tasking, except that we need to pass the executor as an input argument so we can create a task group inside the Fibonacci function. You probably have noticed the difference between task group and runtime in this particular Fibonacci example. When you call co-run from a task group, that co-run is localized to the parent task, while calling runtime co-run can trace back deeply to the first runtime task. To be more specific, a task group's co-run returns as soon as both child tasks 5n-1 and 5n-2 complete, while the runtime's co-run may wait until all child tasks of the topmost runtime finish. As a result, task group's co-run may incur slightly higher waiting overhead, but typically has a better data locality pattern than runtime's co-run. Now, I would like to showcase 2 real-world applications of recursive task parallelism. The first use case of recursive task parallelism is trapezoidal integration, which is a numerical method to approximate a curved area using trapezoid sum. The idea is very simple. We approximate the area under a curve with the trapezoid over x1 and x2. We first evaluate a function at the two endpoints, fx1 and fx2, and approximate the area using a trapezoid, fx1 plus fx2 times x2 minus x1 over 2. Then we recursively refine the estimate by splitting the interval until it converges. When the number of splits approaches infinity, the sum of all trapezoid area will converge to the exact area under the curve. Algorithmically, we start with the coarse trapezoid over the given range x1 and x2. Then we recursively partition this interval to refine trapezoids and stop when approximation is within the tolerance. As you can see in the figure below, this recursive partition naturally forms a binary task tree. There is no shared data among partitioned subintervals. They are all independent. As a result, trapezoidal integration method is an excellent fit for recursive task parallelism. The algorithm has a recursive divide and conquer structure, where the algorithm structure is the same as a recursive task structure. More importantly, RTP can express this structure directly without flattening it to iterative tasks. This code implements the trapezoidal integration using recursion, sequentially. We start with a single trapezoid between x1 and x2, whose area is passed in as a. We then split the interval in half, evaluate the function at the midpoint, and compare the area of the two smaller trapezoids with the original estimate. If the difference is small enough, we accept the result. Otherwise, we recursively apply the same process to each half. The key idea here is that each recursive call works on an independent subinterval, which makes this algorithm naturally suited for recursive task parallelism. This slide shows a parallel implementation using Taskflow's runtime tasking. We recursively integrate trapezoids as before, but now the left subinterval is computed asynchronously. The right runs immediately with tail optimization, and co-run waits for the necessary child data to become available before returning. Each subinterval is independent, so recursion naturally exposes parallelism. This slide shows another parallel implementation using Taskflow's task group. Basically, the implementation is similar to the previous one, except that we pass the executor as an input argument from which we can create a task group. For the same performance reason, we also adopt the tail optimization for one trapezoid recursion. This slide shows the performance of the task parallel trapezoidal integration, where we run over the range from 0 to 1000 on a 16-core Linux machine. In general, the runtime decreases as we increase the number of threads. For example, by using 10 threads, we are able to achieve 7x speedup. The performance saturates at about 8 to 10 threads. The second use case is a parallel merge sort, a classic divide and conquer algorithm that sorts an array by recursively partitioning it to two halves, sorting each part independently, and merging two sorted halves into a sorted one. As you can see from the figure below, merge sort is naturally recursive. There is no shared state among partitioned subarrays, so partitioned subarrays can run concurrently at every level. With these properties, merge sort is an excellent fit for RTP. The algorithm has a recursive divide and conquer structure, where the algorithm structure is the same as the recursive task structure, and RTP can express this structure directly without flattening it to iterative tasks. Let's take a look at an example of merge sort. Assume we want to sort an input array of 8 numbers, 7, 2, 9, 4, 3, 8, 6, 1, with a base case return on one number. At the topmost level, we have 8 numbers, not reaching the base case yet. So we partition the array into two halves, subarray 7, 2, 9, 4 and subarray 3, 8, 6, 1. Then we process the left half, 7, 2, 9, 4. Since the array has 4 numbers, not reaching the base case yet, we will partition the subarray 7294 to 2 halves, subarray 72 and subarray 94. Now, we move to the left half, 72. Since the array still has 2 numbers, not reaching the base case yet, we partition the subarray 72 to 2 halves, subarray 7 and subarray 2. Now, the leftmost partition has only one number, 7. Obviously, a subarray of a single number is sorted, reaching the base case, so we return. When we return to the previous recursion, we move to the right partition, which has only one number, 2. Obviously, a subarray of a single number is sorted, reaching the base case, so we return. When we return from both sides, we got 2 sorted subarrays, and we want to merge them into a sorted one. For the example here, we want to merge 2 sorted subarrays, 7 and 2, into a sorted subarray 2, 7. This is the conquer stage, combining partial results into a larger sorted subarray. More importantly, in C++, this operation can be implemented using std merge with linear time complexity. Similarly, on the right branch, we merge 2 sorted subarrays, 9 and 4, into a sorted subarray, 4, 9. Moving up one more level, we merge 2 sorted subarray 2, 7 and 4, 9 into a sorted subarray 2, 4, 7, 9. Again, this can be implemented using std merge with linear time complexity. We apply the same recursive procedure to the right partition from the top. We merge 2 sorted subarrays 3, 8 and 1, 6 into a sorted subarray 1, 3, 6, 8 using std merge. Returning to the root, we merge the 2 sorted subarrays 2, 4, 7, 9 and 1, 3, 6, 8 into a fully sorted array 1, 2, 3, 4, 6, 7, 8, 9. This completes the merge sort algorithm. This slide shows the sequential implementation using the C++ algorithm library. In this implementation, we set the cutoff at 1024 elements. If the array is smaller than that, we just sort it sequentially. Otherwise, we recursively split the data array into 2 halves, sort each half independently, and then merge the 2 sorted subarrays into a sorted one using std merge. Notice that we use a buffer to assist the merge process as required by the C++ merge algorithm. As you know, merging 2 sorted subarrays efficiently usually needs a temporary buffer to store the intermediate results. This slide shows a parallel implementation of the merge sort algorithm using Taskflow's task group. At each partition level, we create a task group to launch the right recursive call asynchronously, while sorting the left half in the current thread. The task group then waits for both halves to complete before merging the results and returning to the previous level of recursion. Just for comparison purpose, this slide shows a parallel implementation using OpenMP tasking, which is a well-known parallel programming library based on compiler directives. The implementation is very similar to the previous slide, except that the task creation and synchronization are handled using compiler directives. At each level of recursion, we create an OpenMP task to sort the right half of the array, while the left half is processed by the current thread. The task wait directive ensures that both recursive calls complete before we merge the 2 sorted subarrays. The parallel region with a single entry point guarantees that the recursion is initiated only once, while allowing tasks to be executed by the OpenMP thread team. In terms of performance, we sort a vector of up to 100 million elements, comparing Taskflow of 8 threads, OpenMP of 8 threads, and a sequential implementation of 1 thread. We can see that the parallel implementation outperforms sequential execution when the input exceeds 1 million elements, at which Taskflow completes in 1.8 milliseconds, OpenMP completes in 2.4 milliseconds, and the sequential implementation completes in 5.1 milliseconds. If you are interested in learning more about this benchmark, please check out the link below. In today's presentation, We have learned how to program recursive task parallelism in Taskflow and understood the role of cooperative execution in recursive task parallelism. Finally, we presented two real-world applications of recursive task parallelism and gave example implementations using Taskflow. If you are interested in learning more about Taskflow, please check out our project website at taskflow.github.io. You can post your questions on the issue page of our GitHub repository. With that, I'm going to stop here. Thank you very much.